Good afternoon. So here we are with talking about dienes. We have three types of dienes: accumulated, where they're connected to the same central carbon; conjugated, where you can draw resonance structures using them all because they're separated by only a single bond; and then isolated ones, where we have an sp3 hybridized carbon in between two double bonds, or at least one sp2 3 hybridized carbon in between the double bonds. So how can we make a conjugated diene? Well, we learned way back in Org 1 that we could do an elimination, and we can still do an elimination once to form a double bond. If we use T-butoxide, we can grab the hydrogen, form the double bond, kick out the bromine, and form a diene. We can do two eliminations at once with the T-butoxide, where we grab one hydrogen, form the vinyl with the bromine on the next carbon, and then take off the other hydrogen to form the diene, doing two eliminations at once. Nothing fancy, stuff we did a long time ago. So bond lengths between single, double, and triple bonds. We all know triple bonds are the shortest, single bonds is the longest, triple bonds are the strongest, single bonds are the weakest of the three. For conformations of 1,3-butadiene, we have either the S-cis or the S-trans configuration, and these are where it's either cis across the single bond between the two, or trans across the single bond. And of the two, it prefers to be in the S-trans configuration just because of steric interactions, but it will go into the other, the S-cis. Read through all of the talk here about molecular orbitals, and we'll talk a little bit about that later when we get into aromatics, but not a lot. Electrophilic addition. Remember what we talked about back in Org 1, that pi bond attacks the least electronegative atom. So the pi bond attacks the least electronegative atom, kicking out the good leaving good. The least electronegative atom goes to the least substituted carbon. And the reason for this is basically because right here, when the pi bond attacks the hydrogen and you kick out the bromine, you form this cation. That cation wants to be the most stable one, so the most substituted cation. So the less electronegative atom has to go to the less substituted carbon, and then the more electronegative atom adds to that more stable cation we formed. If we take one equivalent of HBr and add it to 1,3-butadiene, we get two possible products. We get the bromine on carbon 3 and the bromine on carbon 1 of the what was the diene. So we have, to get to one of them, or to start the mechanism, the pi bond attacks the hydrogen, you kick out the bromine. So that gives us this cation, the more substituted cation. It's an allylic cation, so we know we can draw resonance structures for that allylic cation, and it can go back and forth between being on the secondary carbon and being on the primary carbon. They're both allylic cations, they're both very stable, and then from there, the bromide can either add to the secondary cation, or the bromide can add to the primary cation to give us these two products. Now from Gen Chem, from organic, earlier in Org 1, we talked about alkenes, and we all know which one of these two is more stable. based on the stability of the alkene product. And this, the one on the right, is the more stable alkene because there's more stuff around it. So that is the more stable product. So that makes this one the easier one to form. So when we look at this, we have the 1,2 adduct where the hydrogen and the bromine added to carbons 1 and 2, or we have the 1,4 adduct where the hydrogen and the bromine added to the 1 and 4 carbon. We can also do this sort of thing with Br2 or any other electrophile to the diene, and we'd get the 1,2 and the 1,4 adduct. So thermodynamic control versus kinetic control. If we do this reaction with one equivalent of HBr at 0 degrees, we primarily get the 1,2 adduct with 71% of the product. If we do it at 40 degrees, we primarily get the 1,4 adduct. So what that tells us is the 1,2 adduct is the one that's easier to form, as we said earlier, so that is the kinetic product. And the 1,4 adduct, which forms at a higher temperature, is the thermodynamic product. So can we draw the reaction coordinate diagram for this reaction? Okay, so we have the energy versus the reaction coordinate, and the diene is a certain energy. It doesn't matter where on there. We're not being specific about energy levels. We're just talking about the comparison between the two. And we go over the activation energy and down to a product, and this is the 1,2 adduct. Now for the 1,4 adduct, what happens is we go over a higher activation energy but down into a deeper well for the 1,4. So I'll color code these 1,2 and 1,4 so they line up above. Now when we look at this, the 1,2 is the one with the lower activation energy, so it's easier to get over the energy barrier to form the product, whereas the 1,4 product is of a lower energy than the 1,2 of the product, so it goes down into a deeper well and it's harder to get out of it. So, but it takes more energy to get over the activation energy for the 1,4, so that's why you have to heat it. Pericyclic reactions, the ones we're going to talk about in class are just the cycloaddition reactions. We'll leave the electrocyclic and the sigmatropic rearrangements. There's some information in here. You can read through it. We won't get into all of that in class. There's not time to cover everything, but I wanted to put it in these notes so you could read through it. So each of these are a concerted process. They all happen at once. There are no intermediates, but we can talk about how it's going to work based on a stepwise process of how we can think about what can go on. So the Diels-Alder reaction, we have a generic one shown at the bottom, is a diene, which must be in the S-cis conformation, and a dienophile react together. 4 electrons move in the diene, 2 in the dienophile. And in this process, we form a 6-membered ring. Okay. The diene is normally electron rich, and the dienophile is normally electron poor. There are cases where it doesn't have to be, but primarily it is electron rich for the diene and electron poor for the dienophile. The diene must be in the S-cis conformation so that both of the double bonds are aimed towards the dienophile. You have to be able to line up the orbitals to form all of the bonds at once. Okay, so moderate temperatures are used in this. You can read through this page also, and we'll get into how it goes on. Okay, so the Diels-Alder, here we have the cyclopentadiene, which can dimerize in the Diels-Alder process to form this product over here. We can heat this and it can fall apart into the two cyclopentadiene starting materials. Okay, so it's a reversible process. In this, the double bond, the groups on your dienophile prefer to be in the endo conformation as opposed to the exo conformation, just because how they line up with respect to the larger bridge and how it lines up with the orbitals on the carbonyls and the double bonds. So it helps it go endo. So primarily it'll be normally have an endo process or an endo product that will be formed. Most of the time it's endo, but it can form an XO1 if things get in the way. So you can look at this. I want to get into the resonance structures. So in this first one, if one of the two compounds is symmetrical, in the second one we have furan. Okay, it is symmetrical, so it doesn't matter how it lines up with the dienophile. We're going to make as we said, a six-membered ring. On that six-membered ring, we're going to have between carbons 2 and 3 of the diene a double bond. So these would be carbons 2 and 3 of the diene. These two carbons of the dienophile end up being over here. So what's off the dienophile? It has a carbonyl off of it, so we need to keep the carbonyl off of it. And then the diene also has that oxygen right here in the middle of between the two double bonds, so we need to keep that. So we need to end up with a bicyclic compound with a double bond between carbons 2 and 3 of the diene. The furan is symmetrical, so it doesn't matter how it lines up. Either way, they're going to get the same thing. If we look at up here on the top, we can draw a resonance structure for the dienophile and send the electrons up to the oxygen, and we get a positive on the carbon, negative on the oxygen. Okay, we can use the OTMS or the methoxy, either one, and draw a resonance structure, and we get to where we have a negative charge on that carbon of the diene, which is going to react with this carbon of the dienophile. So for these to line up in the product, and we'll draw another one of these as we're going along, the diene would have to have this with a double bond in between carbons 2 and 3. The dienophile would have to be this way, so that this carbon, which is this one that we drew a resonance structure with a positive charge on, is down there, and the carbon of the diene that had the electron-rich character to it is right there. So those two carbons have to be connected together in our six-membered ring. So here we have a couple of Diels-Alder reactions where we're asked to show what would the reagent be that would form that. So we need to find carbons 2 and 3 of the diene. That would be these two bonds form in the reaction, so we're going to have to use the methyl vinyl ketone as one of our reagents, and the other one would be the diene with a methoxy on carbon 1. Okay. When we look at the next one, here is our double bond that's formed between carbons 2 and 3 of the diene. Here are the two bonds that are formed in the Diels-Alder process. So we need to have a double bond with cyanides on the same side, because they're both going back, so they're both on the same side in the product. And we need to have a diene that still has that oxygen in it, so it's going to have to be the furan. Now in this last one, it's a little harder because we have two double bonds left over in our product, or that are still in our product. And remember, we said the dienophile is usually electron poor. So we have these two ester groups on here. So that double bond had to come from our dienophile. So our diene has to be the other half of the molecule with the double bond between carbons 1 and 2 and 3 and 4. It still had that carbon bridge, CH2, so it would have to come from cyclopentadiene. And since we end up with a pi bond in our product, we have to start with a triple bond in our dienophile. So read through the sigmatropic rearrangements, the Claisen rearrangement, and then the color to the different compounds. Most organic things are clear, colorless if they're liquid, or if they're solid, they're white. If it has a long hydrocarbon chain with alternating single double bonds, if it's long enough, it'll move into the visible region of the electromagnetic spectra. And we have two examples here, beta carotene and lycopene. Beta carotene is orange, it's the orange in carrots, and lycopene is responsible for the red in tomatoes. And it's all because of the alternating single double bonds of the conjugated system being as long as it is. So here we have another example of the reactions. If we take the 1,3-butadiene and react it with HBr, if we keep it cold, we primarily get this product. If we heat the reaction up, we get the 1,4 adduct, or if we take the 1,2 adduct and heat it to 40 degrees, we get the 1,4 adduct. And remember, we talked about kinetic versus thermodynamic. At the lower temperature, it's a kinetic product. At the higher temperature, it's the thermodynamic product. And in this process, since we still have the HBr around, we can force it to go from the kinetic product back over to starting material and then back to the thermodynamic product, where it gets down in that deep well and it's harder to get out of it.